All right, the first major type of differential equation that we're going to talk about are the differential equations whose solutions are exponential functions, so exponential growth or exponential decay. And so the first example that we're going to talk about is a bank account interest payment. So when we say that a bank account is earning 2% interest, what we mean is if, for example, we start off with $100, then over the course of, we're earning interest, money's being added to the account at a rate of $2 a year. All right, so that's what that means. But that's subtly different than saying that over the course of a year, we will gain $2. And the distinction is akin to, for example, if you're in a car and you're traveling 60 miles an hour, we have a sense that that's talking about a certain speed. We don't necessarily need to say something like, oh, if you're going 60 miles an hour, then that means that in an hour you will travel 60 miles. It's just saying that the current rate of change in position, the current speed is 60 miles an hour. It's the same idea here. When we say that we have a $2 a year increase in our balance, we're saying that the current rate of increase, the current rate of change in a bank account is $2 a year, right? Okay, so when we say something like this, the rate of change in a bank account, in the balance of a bank account, is proportional to the balance itself. What we're saying is that if we currently have $100 in there, then the rate of increase is 2% of that. If we had $1,000, it's going to be 2% of that. So in other words, the rate of change, as in how much money is getting added into the account over time, is equal to some number times the balance itself. So in this case, if we're saying it's a 2% interest rate, this number is 0.02. Okay, so what we have here is a differential equation. And this differential equation encapsulates the information about the way interest payments work, the way the bank account balance is going to change over time. And by solving this, we can come up with some sort of function, some sort of way of talking about what the balance is as a function of what the time is. Okay, so by far, I think, or one of the trickier parts with any of these questions is from some sort of sentence, being able to write down a differential equation. But once we have this, to solve it, we can use our separation of variables technique. So to solve this differential equation, we're going to isolate all of the b parts on one side, all of the t parts on the other side. We're thinking of b as being our balance, as being a function of time. So for a given time, we want to be able to calculate what the balance in the bank account is. All right. So by dividing the b over and multiplying the dt over, we should see that 1 over b db is equal to 0.02 dt. And this 0.02 part, you could bring it over to the left as well, or leave it on the right. The point is that we want everything involving b's on the left, everything involving t's on the right, but you could go either, but the constants could go either way. You'll end up getting the same answer. Right. So once we have this, we want to integrate. The right-hand side, because there aren't any t's here, this is just a constant, becomes 0.02t plus c. The left-hand side, the integral of 1 over x dx is ln of x, so we're just using b's instead, ln of b. And strictly speaking, there should be a constant here, so plus c, but as we've talked about before, the c's are saying these can be anything, so we can combine these anythings into one anything. Okay, so this is a perfectly valid answer to the differential equation. This is a way of representing what the balance is and how that compares to time. That said, it's not a very intuitive answer, right? What we really want is some function b equals things involving time. So we're going to exponentiate both sides, so e to the power of both sides will give us b equals e to the power of 0.02 t plus c. Okay. So this is a little bit better. This is at least saying that our solution is going to be an exponential function, so something that looks like this. But because we have that constant there, that actually is saying that, hey, this could be any one of a number of different exponential functions. And the c is sort of a way of specifying which of these infinitely many solutions is the one that we're talking about. So in our example, if what we're after is some function talking about this particular bank account, right? At time t equals 0, we're saying that there's $100 in the account. What's the function that tells us how much money is in the account for any given particular time t? Well, one way of solving this is to plug t equals 0 and b equals 100 into our equation down here. And then we could go through and we could solve for c. I believe we end up with c equals ln of 100. And again, that's a perfectly valid answer. Again, it's not very intuitive. So we're going to do one more simplification here. We're going to say that b is equal to, well, so just to remember how the exponents rules work, if we've got to get e to the power of a plus b, that's the same thing as e to the power of a times e to the power of b. So we're doing that same thing here. E to the power of 0.02 t plus c is the same thing as e to the power of 0.02 t times e to the c. And remember, the whole point of, sorry, I gotta move this thing down. Okay. The whole point of the c is that we're saying it could be anything. And by specifying a certain constant, we can specify which solution we're talking about. So e to anything is still anything. So one thing we can do is rename this e to the c as some other constant. We could call it c. It's common to also call it something like p0, or in this case b0, e to the 0.02 t. So this thing is a constant. All right. So this is the solution we're sort of after. All right, and the reason that we like this particular solution more is because the way of specifying which of the infinitely many solutions we're using comes down to specifying this b0, which coincidentally, or not coincidentally, like intentionally, is going to be our starting balance. If we plugged in t equals 0 and b equals 100 into this equation, we get 100 equals b0 e to the 0.02 times 0. Well, e to the 0 is just 1. So this whole thing says that b0 equals 100. So the particular solution we're looking for is that our balance is 100 e to the 0.02 t. So maybe this function was the particular exponential function that talks about our bank account that starts with $100.